In this video, we're finding the Maclaurin series for the inverse tangent of x, and we're doing this in a way that I would call brute force. We're finding the Maclaurin coefficients by getting successive derivatives of the function. Now, I just recorded another video where we use a little trickier approach to this by recognizing a geometric series, so you might want to check that out. It's actually a lot faster using that trick. And in this problem, some of the bonus material is that we're asked to use a computer algebra system to quickly evaluate all the same coefficients. So what we're going to find is that the by hand brute force approach is extremely tedious just because the derivatives get so ugly. And this is a good case for using a computer to at least verify your results, if not bypass all the work entirely. Finally, we're asked to show that our series converges at x equals 1, and then we want to use this series to write pi as an infinite series. The reason this is possible is because if I take the inverse tangent of 1, that's the angle whose tangent is 1, that's pi over 4. So once I have this infinite series, I can plug in x equals 1, and I get an infinite series for pi over 4, and then I can just multiply it by 4. So we'll start with just a quick reminder of how a Maclaurin series works. And the whole idea of a Maclaurin series is to say that any reasonably well-behaved function, in particular I want to be able to differentiate it as many times as I want, can be written as a polynomial expansion, provided that I keep infinitely many terms. And in sigma notation, it looks like that. And this might seem like an insane proposal that no matter what function I'm talking about, I can basically write it as a polynomial, provided that I'm able to use infinitely many terms. But the way it turned out, there was a pretty simple derivative trick that allowed us to isolate all of these c's. And I'll post a link to the video where that was derived real quick. And as it turned out, we were able to get those c's by taking the nth derivative of our original function, evaluating it at x equals 0, and dividing by n factorial. So just a little side note on the notation here, that f parentheses n of x, that's the nth derivative of the function. And what I'm going to do in this video is I'm going to keep going, finding the terms of this Maclaurin series until I can recognize the pattern, which to me means I've got to find at least 3 non-zero coefficients in order to see what the pattern is going to be. So I start taking derivatives of the inverse tangent function. And you should be aware that when n is equal to 0 in this formula, that means just the original function, the 0th derivative. So that's where we begin. F of x is the inverse tangent of x. And that means f of 0 is the inverse tangent of 0, the angle whose tangent is 0, and that's just 0. And that means my first Maclaurin coefficient is going to be 0 over 0 factorial, 0 over 1, or 0. So we start out with a 0 coefficient, so that's not very helpful in recognizing any kind of pattern. And I go on to the first derivative. And the derivative of inverse tangent isn't so bad. That's 1 over 1 plus x squared. And when I evaluate that first derivative at x equals 0, I get 1. So it's 1 over 1 plus 0 squared. That's 1. And that means if I go back and look at the formula for the coefficient, Cn, I get a 1 over 1 factorial, which is just 1. So C1 is equal to 1. So we have our first non-zero coefficient. Now at this point, you might see what's coming. If I start taking higher and higher derivatives, things are not going to get nicer, they're going to get uglier. So I take the second derivative by thinking of the first derivative as 1 plus x squared to the negative 1 power, and then I use the chain rule on that. That's the first part of the derivative, and then I have to differentiate the interior with respect to x, which is a 2x. Rewriting it as a single fraction, that's a negative 2x over 1 plus x squared quantity squared. Well, this one isn't so bad to evaluate. F double prime of 0 is going to be 0 because I have an x in the numerator that's going to vanish. And this means C2 is equal to 0. Now things start to blow up a little bit because to get successive derivatives, I'm going to end up applying the quotient rule and then simplifying the result as much as I can. And so I'm differentiating negative 2x over the quantity 1 plus x squared all squared. So I take the derivative of the numerator, multiply by the denominator left alone, subtract what I get by leaving the numerator alone, so there's a double negative there, it's a plus 2x, multiplied by the derivative of the denominator, which requires the chain rule, so that's a 2 times 1 plus x squared to the first power times the derivative of 1 plus x squared. And then this whole thing is divided by the square of the original denominator, which gives me a 4th power there. I can cancel one factor of 1 plus x squared, so that becomes a third power in the denominator, and that one's gone, and one of those is gone. I'm going to distribute across that first term in the numerator, and I get a negative 2 minus 2x squared. And then in the second term, I have 3 factors of 2, so that's an 8, and then an x squared. And that's all divided by 1 plus x squared to the third power. So I get a grand total of 6x squared in the numerator, and then minus 2, all divided by 1 plus x squared to the third. This means f triple prime of 0, subbing in 0 for x, gives me negative 2. And in turn, this means our third coefficient, C3, that's f triple prime of 0 divided by 3 factorial. So I get negative 2 over 3 factorial. And 3 factorial is just 3 times 2, and the 2's cancel. So I get negative 1/3. So this is progress. Now we have 2 non-zero coefficients, and I'm just going to try to hunt down one more. And I think I can fit one more derivative on this page. So fourth derivative of x. Again, it requires the quotient rule. And here's my third derivative in general back here. So I'm going to differentiate that numerator, and I get 12x. Multiply by the denominator left alone. Subtract the numerator left alone. Derivative of the denominator, which again requires the chain rule. So that's 3 times the quantity 1 plus x squared, squared times 2x. And then this whole thing will be divided by the original denominator squared, so 1 plus x squared to the 6th. This time I can cancel 2 factors of 1 plus x squared from the numerator and denominator. So those are gone, and there's only one of these left. And canceling 2 factors from the denominator leaves me with an exponent of 4. And I'll go ahead and distribute the 12x in the next step. So I have a 12x plus 12x cubed, then minus, and I have a 3 and a 2x in there, so it's 6x out in front, 6x, times the quantity 6x squared minus 2, all divided by 1 plus x squared to the 4th. Then in the next step, I'm going to go ahead and try to combine my like terms. So when I distribute this negative 6x on the right-hand side of the numerator, that gives me a negative 36x cubed, and I have a 12x cubed on the left side of the numerator. So 12x cubed minus 36x cubed is negative 24x cubed. The other term I get from distributing is a plus 12x, and I can combine that with the plus 12x all the way on the left side of the numerator, and I get a plus 24x, all divided by 1 plus x squared to the 4th. And I'll just leave it that way for now. You could factor the 24 out if you want. And I see that f fourth derivative evaluated at x equals 0 is going to be 0 because that numerator vanishes. Not surprising, because we've seen for a while now that every other term is 0. And it turns out C4 is equal to 0. Here's a copy of the fourth derivative just for reference, and I think it's going to make our lives a little bit easier now to go ahead and factor that 24 out. I'll write it as 24 times the quantity x minus x cubed. You could even factor an x out, but it's not wise because then you'd have to use the product rule when you differentiate the numerator. I don't want to do that. And I start working on my fifth derivative. So I do the derivative of the numerator minus numerator left alone times the derivative of the denominator. So that's a 1 plus x squared to the third times 2x, all divided by the square of the original denominator. So if you want, you could take the time to simplify this, but my plan is to stop with the n equals 5 term. And it's pretty easy to sub in x equals 0 into this. I can tell that the second half of the numerator is going to vanish because there's a factor of x stuck to it. Even this term vanishes in that second half. So definitely all of that stuff is gone. And then when I plug in x equals 0 into the left half of the numerator, that's just 24. In the denominator, I just have 1 to the 8th, or 1. So my fifth derivative evaluated at x equals 0 is just 24. You might notice this is 4 factorial. And my n equals 5 Maclaurin coefficient is going to be the fifth derivative of our function evaluated at 0. That turned out to be 4 factorial divided by 5 factorial. But 5 factorial is just 5 times 4 factorial. Those cancel out, and I get a positive 1/5. So that's my third non-zero term. And at this point, you should be able to detect some kind of pattern. When I plug those c's back into our original proposal, that we could write our function as a polynomial expansion, it turned out that C0 was equal to 0, C2 was 0, C4 was 0, and C1 was just 1, so I'll go ahead and put that in. C3 was negative 1/3, and C5 positive 1/5, and I can definitely see the pattern here. And now I can go ahead and put this in sigma notation. I'll go ahead and start at n equals 1. It just seems like the most natural choice. And I've got to start with a positive term, so I'm going to put an exponent of n minus 1 on the negative 1. That makes the first term positive, the second negative, and so on. And then we get x to an odd power starting with 1. So I can accomplish that with a 2n minus 1. When I sub in n equals 1, I get 1. When I sub in n equals 2, I get 3, and then 5, and then so on. And then I want to divide by that same odd number, so that goes in the denominator. So there's my infinite series representation, in other words, my Maclaurin series for the inverse tangent function. So that was a really tedious process just to get us the first 3 non-zero coefficients of the Maclaurin expansion of this function. So I wanted to illustrate real quick how we could use a computer algebra system to at least check our work, if not bypass some of the work, depending on the context that we're working in. All right, so we're working in the computer algebra system WX Maxima here. This is a free and open source computer algebra system. And you could just type in, give me the derivative of the arctangent function, and then give me the second derivative. You would just put a 2 as the last argument of the diff command. Give me the third derivative, and so on and so on. And there are even commands for cleaning up the appearance of those derivatives. I decided to get clever about it and put this inside of a little loop structure. So I have, for I from 0 through 7, do, and then here I'm defining my derivative. So f of I is the derivative of the arctangent function with respect to x, and then I tells me the order of the derivative to take. That starts from the 0th derivative, which is just the original arctangent function, and then I went all the way up to the 7th derivative, which is more than I did by hand so far in the video. In my next line, I want to compute one of those Maclaurin coefficients, c of I. So what we do is we substitute 0 for x in the expression of the ith derivative, just like we did by hand, and then we divide by I factorial, and I get my ith coefficient c, and then I tell Maxima to print out the result for all these i's from 0 through 7. So when I hit Shift Enter, it'll only take a fraction of a second to do what took probably 10 minutes in the video. I get that my first coefficient is 0, the second one is 1, and then 0, and then negative 1/3, 0, 1/5, 0, negative 1/7, and so on and so on. Now some of you might realize there's actually a built-in Taylor polynomial algorithm in Maxima, but I didn't want to miss the opportunity to write a fun little loop. All right, so back to the original problem. And to wrap things up, we're going to find a way to express pi as an infinite series. Now we could use the ratio test to find the interval of convergence for this. But in this particular problem, I'm just interested in one particular point, and that's when x is equal to 1. And again, the idea is the inverse tangent of 1 is pi over 4. That's the angle whose tangent is 1. And that allows me to relate pi to this infinite series that I would get by replacing x with 1. But we need to be careful and actually show that that series on the right-hand side is going to converge. Well, that's an alternating series, and actually it looks like a very close relative of the alternating harmonic series, so I'm pretty sure it's going to converge, but we'll prove it using the alternating series test. The first thing we do is show that the large n limit of the terms goes to 0. And there's really nothing to do here. I can see the denominator is becoming infinite, the numerator is 1, so this clearly goes to 0. The second thing we have to show is that the next term is always less than or equal to the previous term. So let's look at the n plus 1 term. And I can tell that denominator is bigger than the nth term, but to really highlight it, I'm going to find the nth term in there. I distribute and get 2n plus 2 minus 1. So that's 2n minus 1 plus 2. 1 over 2n minus 1, that's an. If I add 2 to the denominator of something, it definitely makes it smaller. So this is less than 1 over 2n minus 1. And I've shown that the next term is always less than the previous term. This allows us to conclude that the series converges. And of course, we see that it converges to pi over 4. So as our final step here, we're going to write an infinite series representation of the number pi. We just multiply both sides by 4, and I get 4 times the sum, as n goes from 1 to infinity, negative 1 to the n minus 1, over 2n minus 1. So we have a new way to write pi. If you want to view it in expanded form, just sub in n equals 1, 2, 3, and so on until you see the pattern. So if we add up all these numbers, 1 minus 1/3 plus 1/5 minus 1/7, and then multiply it all by 4, we get pi. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.